Okay, so I heard somebody talking about sugars. You had that biology test, and you had to talk about, like, what is it when you put two sugars together?
It was actually three sugars by hand.
Yeah, what was the question? Do you remember?
What was the chemical formula after you combined the three glucose?
Yeah, okay, so give you, is this like I can talk about it? Are you guys taking the test still today? Just took it? Okay. So what's the process of breaking sugars apart? It's hydrolysis, right? Dehydration is the other part. Yeah, it's going the other way. So if you know that when hydrolysis breaks it apart, when you put them together, you just pull a water molecule for every two that you put together. So you got first two get together, you pull a water molecule out. So you take out an H2O, and then the second two get together, and you pull out of water. So that's the three. So you have to take C6H12O6, multiply everything by 3, and subtract 2 waters out of it.
So then you take a hydrolysis from hydroxide from one side.
Yeah, an OH from one side and H from the other. Pull that out. That's where the bond is created. That's hydrolysis. But we talked about it here too. So, anyways, we got all on a tangent yesterday. I should have recorded yesterday. It was a good example of me going off on tangents. But we talked all about kind of biomolecule, because they're going to take the test right after. So we couldn't avoid talking about like biology and chemistry. And, yeah, it's all good stuff. So we had a great time. But anyways, so yeah, hydrolysis is the process of breaking water. Dehydration is the reverse of that, like when you pull water out of a molecule to form a bond. So how does hydrolysis work? So what I'm going to try to do is try to draw you the picture and be real consistent about it, about how we think of hydrolysis as chemists. Okay, so first of all, you have to start with a Lewis structure. Let me get a better pen color. I'm going to start with water because I just want to put the water on this side because I want to. So we're going to be talking about this reaction here. And remember, this funny symbol here, that's the equilibrium arrow that I don't have time to keep reinstalling fonts all the time, so I'm just going to leave it and you're just going to have to go with it for now. All right. There's the Lewis structure for water. Anybody know what the Lewis structure for Cn minus is? Like, kind of know it? Yeah, it's got a triple bond, okay, because it goes like this. Yeah, cyanide, yeah. The only reason I thought maybe somebody know it because it's cyanide, not because you're supposed to know it, right? Maybe I don't want you to know it. Okay, and there's the negative charge. So that's the negative charge on the cyanide. So when you do hydrolysis, what you actually do is you steal the hydrogen away, and you're going to form HCN. HCN is going to look like this. So that's the Lewis structure for HCN. And if I steal a hydrogen away from this is Bronsted-Lowry acid-base theory. We were talking about that the other day, right? So this is going to be the donor. This is the acceptor. This is the conjugate base of HCN. But what am I going to get out of that? I'll get an OH minus, okay? And then I'll show you how it happens. And this is how I want you guys to think about it, although I will be perfectly honest with you. The book doesn't really do it this way. Not very many general chemistry books do it this way. Okay, so how did I get that, right? The CN is going to take this hydrogen so you'll notice I started the arrow starts at the electron. That's the start, and ends on an atom. So I'm going to form a bond there. This is Lewis acid-base theory that you had mentioned earlier. When you bring a pair of electrons in Lewis acid-base theory, you're going to form a bond. And when that bond forms, how many bonds can hydrogen have? One. So it's got to get rid of that pair of electrons. Otherwise, it'll be bonded to two things at the same time. Here, let's do this. I see everybody looking at the bottom of the screen. Okay. All right. That's the nice thing about having it all recording. You just throw stuff around. Okay. So, all right. So, what ends up happening is the pair of electrons that was here, okay, so this pair of electrons, oops, sorry, gotta go like this. This pair of electrons that was here goes back to the oxygen. Since the oxygen picked up the electrons, it has a negative charge. The cyanide, which had the negative formal charge before, picked up the hydrogen. Now remember we call these kind of reaction in Bronsted-Lowry theory, it's called something transfer reactions. What do we call them? Proton. Yeah, proton transfer reaction, right? So really what happens is with this negative charge, the cyanide is picking up a proton. Protons have positive charge, right? Cancels out the charge. So you see in the HCN, you don't see a charge. So proton transfer, you can look at it, like again, we're talking about it in two different terms. It's Lewis theory as an electron donor, but we're also talking about proton transfer, which is Bronsted-Lowry, right? And this is the process of hydrolysis. So what happens is the cyanide wants to get this hydrogen, does a proton transfer, breaks the water. That's what hydrolysis literally means. You're breaking a water apart, and so you end up with HCN and OH minus. Okay? This is something that happens anytime you put the conjugate base of a weak acid into water. Okay? Conjugate base of a weak acid placed in water will cause hydrolysis.
It will create a water molecule.
Will break a water molecule. Conjugate base of a weak acid. So you have to think, let me go through it.
Okay.
So I'll get into a little bit more about this, but this is the conjugate base of a weak acid. Remember I said you got to get good at recognizing conjugate bases, acid-base pairs. So if I give you the formula for an acid and it's a weak acid, you should be able to right away write the conjugate base out. The reason I want you to do that is because you're going to get problems where it's going to be part of a formula and you got to be able to spot, oh, that's the conjugate base of a weak acid. What is it going to do to the solution? Okay. So I'll do some examples of that in a second. Well, why is it going to do that? I mean, now we got over the fact that it's going to do it. Just get over it. Okay. Why is it going to do that? Right? Why doesn't it work with a strong acid? Okay. So probably you guys can get tired of me doing this over and over again.
The conjugate bases of strong acids fully ionized.
Yeah, it's like a you can't do it kind of statement, right? Like we're going to make that. Well, you can't make that. Well, I guess then we're not going to do this because, okay, and I'll get into why that statement might make sense. My statements don't always make sense. So what's the conjugate base of nitric acid, HNO3? Yeah. That's NO3 minus, right? Yeah. So I'm going to take NO3 minus. So this is what we're looking at. I'm going to add it to water. And if hydrolysis occurs, there's a pair of electrons on an oxygen that would go over and grab the hydrogen from the water, split the water, proton transfer reaction. Okay, it's a long way of saying that. And I would form HNO3 plus OH minus. So then I get asked the question, right? HNO3 is a strong acid. What do strong acids always do? Completely dissociate. So you can't do this. It won't stick, in other words, okay?
Oh, because as soon as it goes on there, it's gonna come apart.
Yeah, so it's going to happen like for a little bit, and it'll be gone.
Yeah.
And in terms of equilibrium, it just so far favors the left-hand side being dominant, like
Yes.
this is the way it goes, that this isn't going to happen. Okay. Then the question is, go back, think about why does this happen? Because this is what kind of acid?
That's a weak acid.
It's a weak acid. What do weak acids have a tendency to do? Stay together, right? So when you put these things together, then what happens when you put water and cyanide ion in solution together, what ends up happening is the HCN forms, and it likes to be formed. A simple concept, and I like to oversimplify things sometimes, it happens because HCN is stable and HNO3 is not. Right? HCN is stable. That's why weak acids stay together. If they had been unstable, they would have fallen apart. So nitric acid tends to be less stable than HCN. Okay. Okay.
And this holds for strong acids, period.
Yeah,
and weak
all
acids,
strong
period.
acids, right? No hydrolysis. All weak acids, conjugate bases, hydrolysis. Okay, so you can take a picture, Wade.
Well, it looks good.
Oh, I know, but I'm going to move to the next slide. Yeah, question.
Isn't this like neutralization basically? Go back.
It's kind of like neutralization backwards, right? So you would expect this to go that way, right? So it's going to be really favored. You can actually, for a lot of these reactions, like even for like this one at the top, you can even calculate the equilibrium constant by combining equilibrium constants. Okay. Okay. So let me go on and finish the stuff that's on the next slide. Actually, so let me go to the next slide. Okay. So if the hydrolysis is going to take place, you know, we talked about acidic and basic. So in neutral solutions, so if I say pure water, right? I would say, what's the hydroxide concentration, or what's the hydronium ion concentration? What is it? They're the same, and at 25 degrees Celsius, you can calculate what it is, and it's 1 times 10 to the minus 7, okay? So, but they're always the same. In neutral means acid concentration, hydronium and hydroxide are the same concentration. Now, we always say 1 times 10 to the minus 7, but I told you guys yesterday, endothermic reaction, temperature goes up. Those numbers both change, but in a neutral solution, they're always the same. Okay? That's the concept. So if I do this, if this happens, what happens to the solution? What? No? You're getting tricked. That's the what happens in people's head. They say, "Oh, I made an acid; it's going to be acidic," but acids are only acidic when they ionize. All right. What did this form when it was formed? Hydroxide. When we talk about acidic and basic, right, we're actually talking about the free hydronium and the free hydroxide. It doesn't have, I mean, it's related to this, but that's just because that is formed in solution doesn't mean the solution's acidic. That's kind of a hard one to if there's an acid formed in solution, your first inclination is to say it's, yeah, right? That's why you said it, right?
Yes, but
Yeah.
it's not disassociated.
It's not dissociating acid, and acidity is based on hydronium and hydroxide, and so you're forming hydroxide when the HCN, the weak acid, pulls the hydrogen off the water. You're forming OH minus. So hydrolysis, okay? Go ahead.
It's kind of preventing hydronium from being there.
Kind of preventing hydronium from
Because
being
we
there.
know that water self-ionizes into hydroxide.
Yeah.
So that acid's taking all those hydrogens.
Yeah, taking all those hydrogens, and so what ends up happening, you get more OH form. It's a Le Chatelier kind of. Yeah.
Okay.
So if you think about it as a Le Chatelier thing based on the idea of self-ionization of water, the other way to think about it, which is good, All right, that's self-ionization going on like that. Right, adding the Cn minus is going to strip away hydroniums. As it strips away hydroniums, what happens to the equilibrium? Shifts. That, sorry, it's hard for me. I had to wrap around my head to get there. Goes that way. Goes the product side, that more of that's going to get made and becomes basic. So you can look at it either way. Okay. In the sum of things, it's about the same. You know the really easy way, though, to know that? I mean, this sounds, I'm going to just tell you this, and you're going to be like mad at me for not maybe saying it first. When you put a base in solution, what do you think happens to the solution? You make it basic. But it's through hydrolysis that it's happening. Okay. So having thought through all the process of how it happens, just remember, hey, I put a conjugate base of a weak acid, it's a base. The solution's going to be basic. If I put the conjugate acid of a weak base in, it should be acidic, right? Okay, there we go. Now, we're going to get to the problem later. If you have the conjugate acid of a weak base and the conjugate base of a weak acid, and they're together in one compound, and you throw them in solution, you can't just say, oh, it's going to be acidic or basic, because one wants to make it acidic. Yeah, it's going to blow up. One wants to make it acidic, one wants to make it basic. And you actually have to do a calculation or analyze structure to figure out why that is. Okay. There, I said it.
Would it be, I think in that situation, if you had a weak acid,
Uh-huh.
so the conjugate base of a weak acid versus the conjugate base of a strong acid, the weak acid will win out.
Yes.
Yeah, because it's strong.
Because the strong isn't going to do anything, but the other one, yeah.
Okay, I get it.
Yeah. But if they both have equilibrium constants, if they're both weak, you figure out which one's stronger.
The weakest, right?
The
One with the
if you're looking at Kas, it's the weakest will
yeah,
win.
the
Yeah.
weakest one.
Yeah. If you're looking at,
The weakest one is the most strong.
we'll get to it. I'll make a little table where you just like, oh, if it's this and this and then it's that. Okay. And we can do most of it right now, but we haven't covered enough material to really go on into it. So, all right. So let's talk a little bit about acid-base strength. I'm just going to go with the slides. I didn't want to do this right now, but I thought, let's go with the slides because I thought through this at one point in my life. So what we're going to do is the title of this section is a little bit intimidating. Structural determinants of acid strength, right? All that means is we're going to look at what makes acid strong or weak. Okay? But we're going to look at the structure. So this all has to do about Lewis structure, sizes of atoms. These things are all important, okay, in determining acid strength. These are some of the things that we're going to be looking at. Size of the bonded atom, okay? How polar the bond is, that's also important. And then we'll go through these things one at a time. Resonance. You guys remember resonance where the bond moves around? So we'll review a little bit of resonance as we go through this. Inductive effects, I don't think most of you know what an inductive effect is. But an inductive effect is what's known as a through bond effect. And so let's say Sergio, who's over here, and Brenda, there's a single bond there, and we're atoms, right? And there's a single bond here. If I pull all of Brenda's electrons over here, like I'm really electronegative, okay? Then Sergio is going to feel an effect because that creates a charge on her. So that's a through bond effect or an inductive effect, okay? So that's what that, I'm going to write that down. Hang on a second. Through bond.
Like the beakers with the.
Yeah, like the three beakers. If I pull water out of one, right, it pulls water out of the middle one, and it pulls water out of the other one, like a coupled chemical. Yeah.
Is that like
It's like dipole. Dipoles are, the difference in electronegativity between two atoms creates a dipole. The dipole can have an inductive effect. That is, you create a charge in another atom in a larger structure, and that charge affects the behavior of the atom next to it. Okay, yeah. And there's two kinds of inductive effects. One makes the acid stronger. One makes bases stronger. One's a donating electron withdrawing effect, we call it. And one's an electron donating effect. So what do you think an electron withdrawing effect is? Pulling away electrons. So more electronegative atoms, more being more than what it's attached to, more electronegative atoms will cause an electron withdrawing effect. And then charge, the amount of charge something has an effect on how strong the acid is. So what I want to do is now go through all these things, okay? I think if there's any term up here that you don't like remember really well from like Chem 1A and you want me to go over it any time, we just stop and we go over it so you guys can know what, So we're all like at the level you need to be to understand. Okay, so for binary acids, the size of the atom, the anion, okay, is important, and the electronegativity of the anion is important. And these two effects, okay, are on the periodic table, right? Size of anion varies significantly as you go vertically in the periodic table. So like this. Remember, these are periods. These are groups. I'm just going to put GR. And if you remember the trend for, again, this is going to be for size of anion, right? Where are the biggest atoms? Bottom, and then left. Okay, but we're just looking in groups. So for now, I mean, the biggest atoms, the atomic size trend goes like this. A lot of times people will draw it as going from here this way down, but since I'm focusing on the group behavior, I'm going this way, and these are largest. But the left-right trend is fairly subtle. It's the vertical trend where you get jumps in the energy levels, the N levels, and every N level is much bigger than the next. So that's the idea. Okay. Okay, so now, electronegativity is a trend, right? Where is the highest electronegativity? Top right. Fluorine over here, right? So electronegativity trend is along a period that has the most influence on how strong an acid is, whereas size is the most important trend going vertically. So we look at two different things. We're talking about two different things. So now, back to definitions. What's a binary acid? Binary's two, right? Two kinds of atoms, right? So yeah, so let's do HF, HCl, HNO, sorry, let's not do that. HBr, HI. And then the last one, this acetane, there's so little of it, I never usually include it, but they say like there's a gram in the earth, it's radioactive, so it gets formed. Yeah, you're not gonna be doing a lot of chemistry with it. Although they have done chemistry with it, that's how they know its properties fit where it fits too. Okay, so which one is the biggest? I, yeah, IHI, right? It's going to be the biggest. Iodine's the biggest. Turns out that's the strongest acid. So the strongest acid's at the bottom of the group. So if you have any binary acid, two-atom acid, the strongest acid is always at the bottom of the group. So let's think about this, all right? Here's an H plus. Oh, you know what? I'm going to make it blue. I love using blue for positive. There's my H plus, okay? Okay, there, it's moved him. And I'm going to have an anion that goes with it. And anions are usually red, but I'm not going to make it pure red because it's kind of annoying. So let's say that's HF. Hydrogen's really tiny, by the way. So it's probably not even drawn to scale, but it's probably pretty close. If I were to do HI, all right, the I would be the same, or the H would be the same, but the I would be like this. Well, at least that big, actually. Like that. Okay, so what do you know about bond strength and bond length? What do you know about those things? What do we usually say? Shorter bonds or stronger bonds, right? Which one of those has a shorter bond? HF. Right? So that's one thing to consider. HF has a shorter bond. Why does it have a shorter bond? Because bond, really what the electrons from the hydrogen are trying to do is get close to the protons of this nucleus. Can't get as close over here.
Measured from the center.
It's measured from the
Just like
center.
Newton and measured from the center of the earth.
Yeah. Just like when they did planetary forces of attraction, they always measured from the center of the body. They call them bodies.
Yes.
Center of the body to another, right? One to another. So think about this, okay? If this is a stronger bond, what does that mean about acid strength, the ability to donate protons? It's a weak acid. Okay. So things that, like if you had binary acids, like H2O is a binary acid, you don't think of it that way, right? Because we think of it as neutral. But if it's a binary acid, it's weak, right? In comparison to like H2S. Because H2S, sulfur's bigger, right? So it is easier for the hydrogen to be removed than it is in H2O because the hydrogen is closer to the nucleus of the oxygen.
So that's why the strong acids disassociate.
I might be able to understand.
Strong acids disassociate fully because part of what we're talking about now has to do with charge, and it's the stability of charge. So we think of things as, oh, this is stable, this is not stable, but it's a relative behavior. Okay, bigger atoms tend to have more stable charge because what happens? Well, the bonds are easier to break, but that's an after the fact kind of thing. But they're bigger atoms. Atoms, when they make ions, are more stable because they can spread the same amount of charge around a larger area. If you've had physics and you put a charge on a sphere, where does the charge sit? Sits on the surface of the sphere. That's why, like when I take a balloon and I rub it on, I like doing these demos, rubbing a balloon on my head. It's like one of my favorite things. And what does it do? It'll stick to almost any surface. But it turns out, you can try this. The charge spreads around the balloon, even though it's not very conductive. You could I could rub it on this side and stick the other side on too. Because what's happening is the negative charges don't like each other, the electrons. And so what they tend to do is push away from each other. The farthest away you can get in a sphere is on the surface. So charge distributes on the surface. So this charge density that's on the outside, this extra charge, which is out here in an orbital, right, spreads further and causes it to be more stable.
You know, the electrons in electricity run on the outside edge of the wire.
Yeah.
Same kind of thing, isn't it?
Yeah, that's true. So, and you'll learn this in physics too. If you have a cylinder, the negative charge is distributed on the outside as it
Well,
conducts.
like electric wire.
Yeah. So if you're inside the field, like, right, you don't have any charge on you. The charge will be around you on the surface.
There's a guy getting in the barrel
Yeah.
with the electric charge around the outside.
All right, we're gonna get back to this. It's a good idea, but so charge is distributed on the outside. More stable anion, this is a very important concept, more stable anions make stronger acids because they can dissociate from the proton. Okay? More stable anions make stronger acids. The anions are the conjugate bases, right? More stable conjugate bases make stronger acids. I'm going to say CB equals stronger acid. Not strong, but stronger. It could be strong, but I want to do it in a relative context, okay?
They lose the hydrogen more easily.
Yeah. Okay, so let's talk. So that's, like, if I did do this. Now, you don't usually think of ammonia as an acid, but in organic chemistry, you can use it as an acid. It's very weak. But which of H3P or H3N, which would be a stronger acid? H3P, right? Just because it's bigger, it distributes the charge better. That's an example of something as a binary acid, right? The other thing that affects acid strength, I'm going to wipe this slide here. The other thing that affects acid strength is electronegativity of the anion. And more electronegative anions make for stronger acids. Okay? Make for, stable anions, stronger acids. More electronegative atoms are more stable anions make for stronger acids. I'm going to call it the conjugate acid, but I'll just say acid. So, for example, if I have I did it again, I'm writing at the very bottom of the screen. If I have HF versus H2O, so same period, right? Second period. Oxygen and fluorine right next to each other. HF is a stronger acid because the fluorine is more electronegative. Okay. Does that really answer like why it's a stronger acid? So if you really want to know why it's a stronger acid, you have to think back as why is it more electronegative, right? You remember what's different about the nucleus of oxygen and fluorine? I mean, just how many of each subatomic particle does oxygen have and fluorine have? Well, oxygen's got 8, 6, what is it, 6? 8 protons, right? Oxygen 16 would have 8 neutrons, right? And then fluorine has 9. More positive charge makes the electrons more stable, stronger acid. All right? More positive charge to stabilize the negative charge, because when both have a -1 charge, the fluorine has more positive charge to stabilize that, and as a result, ends up being a stronger acid. Okay? So left to right trend, okay, strongest acids on a period are to the right vertically, strongest acids are at the bottom in a group, okay? For binary acids. It's really warm in here to me. I don't know if it's just, it is warm in here? It's either that or I'm dying of fever or something. Could be both.
Could be both.
Yeah, yeah. You never know. But if I do die, I'm canceling class, just so you know.
All right.
Yeah. Hey, I'm going to leave you with something good when I go.
Yeah.
I could also just assign more homework. I'm dying. Where's Mastering Chemistry? Assign everything. There's a button for that, maybe.
The exit button.
Yeah. I always say that I'm going to tell a joke. I think I've said this before. I'm going to die in class, probably. It's the most likely thing. I know it's kind of morbid. But I'm going to start a joke, and then I'm going to go. Never hear the punchline. It'll be one of those jokes that doesn't have a punchline. It'll be going, well, what's the punchline to the joke?
That's the joke.
That's the joke. It's on you, yeah. Yeah. Okay, so oxo acids. So I want to review a little bit on Lewis structures of oxo acids because I know most of you on the review sheet got it wrong. That little review sheet tells me so much about, like, oh, this is what I got to talk about. So I'm going to start a blank page here. I'm going to talk a little bit about oxo acids, and we're going to throw resonance in there because I know we have to review that, because that's the other thing on those Lewis structures. I just had you draw a couple, and people just goofed it all up. So you suddenly is the stove on? Okay, good. Then we're not stopping. So so let's say I talk about nitric acid, because that is actually the one that was on that worksheet. So HNO3. And I say draw the Lewis structure. The first thing you got to do is give me a good skeleton for nitric acid. And this is oxo acids in general, okay? Oxo acids, the hydrogen is connected to an oxygen, not the central atom. So if I'm going to do a Lewis structure, then the first thing that I have to do is I have to draw the skeleton, and now that I know the H is on an O, then I can put the nitrogen in the middle, that electronegativity thing that they talk about, least electronegative is in the center, or I talk about one with the most unpaired dots in the Lewis dot structure is usually in the center. So carbon, if you have carbon, is usually in the center. And if you have nitrogen and it doesn't have carbon, then the nitrogen's in the center. If you have oxygen, then the oxygen, whatever has the most dots in the Lewis dot. Do you know what I'm talking about? Yeah. Like Lewis dot for carbon has got 4 dots, right? Group 4, 4 valence electrons, 4 dots, that's usually in the center. That's why in biochemistry and biology, carbon is like always the middle of a structure. Okay. So here we go, HNO3. Put the oxygens around it. And then I have to put the hydrogen on. Hydrogen's got to go on an oxygen, so I go like this. Then putting it on the nitrogen would be wrong. There is actually only one acid that's common to what we use where there's the hydrogen on the central atom.
Oh, that's the ammonia.
No.
Oh, well,
Do you want to know what it is?
sure.
I'll tell you later. So second thing, or at the same time, we've got to count valence electrons, right? So oxygen has 6 valence electrons, and there's 3 of them. So that gives me 18.
Is there a lone pair on the nitrogen?
Well, yeah, but we're not there yet.
Oh,
We're just counting valence electrons. We're going through the, so that's okay. 1 nitrogen, times 5. I'll call that 5. And hydrogen, 1. Woohoo, 1 times 1. Shh, slow down. Killing me. Okay, I'm kidding. So then what you do is you subtract all the electrons you've used already. Well, what electrons have you used already?
Bonds.
The bonds. How many bonds are there? 4. So 4 times 2, it's 8. Okay? So I'm going to subtract away 8 because that's how many I've used. So that's 4 times 2. Leaves me with 16. And then you distribute the electrons, most electronegative atoms first, which in these, it almost always is outside atoms first, and then you go to the inside and you drop the electrons. So, yes, nitrogen will have lone pair. So we go like this. And don't do any double bonding yet. This is where everybody's like, oh, I'll put double bond right now, and I'm cool because I drew a double bond.
Slow down.
Yeah, slow down. Just take your time. You'll get it right. If you do that, you'll probably get it wrong. 1, 2, 3, 4, 5, 6, 7, 8. So why did I do those lines? Those represent pairs of electrons rather than drawing the dots. Okay. I don't know if you guys learned that or not before, but rather than counting every electron, just draw a line. Okay. And people think, well, you know, why would you do that? That's not how you draw Lewis structures. You know how Lewis drew Lewis structures? With lines.
That's right.
Because he thought, I don't want to draw all these dots.
Yeah. See how I was.
But his lines actually, which I thought were cool,
Or the opposite.
I can bring the book in. I have like a book that written by Lewis from like the turn of the last century, right? So it's really cool. It's an old one. It's Lewis structures on Lewis structures.
Yeah.
If he had a lone pair, so like let's say we did ammonia. If he had a lone pair, right, we would do that, okay, or that. What Lewis actually did was this,
Yes, that's right.
because he knew it could make another bond. So then, if you wanted to make the other bond, you just had to put the atom on there, and you were done. Right? He didn't. Probably did. I don't know. Maybe they hadn't invented erasers yet. I have no idea.
But it has, he says it has potential to.
Yeah, it's got the ability to make bonds. I'm just going to draw that all the time. So this oxygen would have had a line going up and a line going down. Anyways,
Yes.
you don't need to know all that detail. We draw them sideways because we're pretty sure it's not going to make a bond. Okay, so I got all my electrons distributed. I did them 2 at a time because I'm lazy. Hang on. Check octets. Yeah? So we're going to check octets. Nitrogen is unhappy. You see this nitrogen here?
Yes.
All right? 2, 4, 6, not happy. We did that intentionally to nitrogen. We cheated it because we gave it electrons last. We said, hey, if we have any left over, you're going to get them. All right? That's like when you have 6 kids in your house, you buy 2 buddy burritos, said, let's split it up, but if you're not here, you'll get the leftovers.
As if there's gonna be any.
Did that last night. 4 children, 2 buddy burritos, pot of rice. Actually, there was leftovers. If you're ever in Reedley, go to Juanito's. They sell get the giant buddy burrito. They're just like huge. We're talking about food, sorry. Fed a family of actually 4 and me, and my wife came over and ate leftovers. Came home and had leftovers. Yeah. Monstrous thing. We got to make a pot of rice. So anyways, so this guy, no leftovers for him, right? So he needs to satisfy his octet. So this is what happens usually in a house like this. One of these guys will share. Right? So I got to bring a pair in and form a double bond. This is how we know when we have to do a double bond. We distribute the electrons. Somebody didn't get anything to eat, so you got to give them. You got to share. And the most logical people to share are these guys here, it turns out, because of formal charge. So we'll get to the formal charge in a second. Oops, I didn't mean to do that. So I'm going to, I know you guys aren't going to like this, but I'm going to do it anyways. So I redrew that. Sorry. This is just so you can see the sequence. And this is a video, right? So you're going to be able to go back and look at it. And then I'm going to get rid of that with my eraser. And I'm going to do that. And now everybody's happy. Well, no, hang on. But everybody's happy in terms of octets. But I didn't have to do it that way. could have done it a different way. In fact, there's a couple of different people that can share here. And the other one is to do this. What's the other one? The other oxygen, right?
Yes,
Does that make the other
although you
oxygen
got the
stable?
hydrogen bonded to it somehow, you can do that.
Was that
Does that make that oxygen less stable?
the negative charge on it?
The ones that you took away the pair from?
No, because it's still got 8. Okay, we'll figure out what makes it less stable when we do formal charge, and we'll sort of talk about what's going on. Okay, so I'm going to redraw this one. I'm going to erase this here, and I'm going to do this. Okay, so those are all 3 are valid Lewis structures that satisfy the octet rule, and this is when we bring up the idea of formal charge. And the idea of formal charge is you want to have less charge distributed on the structure for the best structures. What do we mean by best? And actually what we're saying, the best structures are the most stable ones. So if you think about charge and separating lots of charges out, right? It takes energy to separate positives and negatives from each other. So if it has a lot of formal charge, what it's actually saying is you've separated a lot of charge from each other, and that's making it less stable. That structure is not as good. So we have this concept of equivalent Lewis structures or resonance structures. Equivalent structures have the same stability. Okay, so I'm going to go ahead and do the formal charges on this real quickly. This oxygen, let's do this oxygen here, because once you do one of these, you got them all, basically. What's the charge here? Well, it's 6 valence electrons, okay? Minus, and most of you learned probably 1/2 the bonded electrons, which is the bonds. So we're going to count bonds. So we're going to go 1 minus the lone pair electrons. You count all the lone pair electrons because they're not being shared with anything. Okay, so 6. Because that's the 2, 4, 6, that from 2, 4, 6. Internet's slowing down, so the pointer's getting a little herky-jerky. Okay, so that's what? -1. Okay, so that's got a -1 charge. Now, I know nitric acid is neutral overall, so there's got to be a +1 charge somewhere. That's actually what I'm seeing when I see that. And so the plus charge is going to be the nitrogen. And I'll tell you how I recognize this. I tell people 1A this, but I'll see how many people remember. So that one is going to be 5 minus 4, because it's got 4 bonds, right? Minus 0, so that's +1. So there's a +1 here. Now I can go and assign this bottom one by analogy. I can say, oh, well, that's the same as this one, and this is the same as that one. So there'll be a minus and a plus. So the positive charge stayed on the nitrogen. This other structure is going to be like this: minus, minus, plus, because I can do those by analogy. They're the same as those other ones. Now, if I see minus, minus, plus, that's -1, right? I'm missing a +1. The +1's got to be this guy here. And we can verify that. It's 6 minus 3 minus 2. That's 1. 6 minus 5. Is that a good structure? Not a good structure. Not a good structure. More charge distributed, less stable. So the equivalent resonance structures, now these are all still valid resonance structures, but the ones that are most stable are these two. We usually separate them by a double-headed arrow, and when it's resonance, we put a bracket around the whole thing. Any questions on that process? Because we're going to expand on this. Okay. Watch the video. If you have questions, come back and ask questions next time. We do have class. You do have class tomorrow and Monday. In my calendar, it says it's President's Weekend.
Right, it's the following weekend.
It's the following weekend. I screwed that up real good. I thought about just taking the holiday anyways, but dang it, another holiday. Oh, it was an accident? Well, it's in the syllabus, right? They always tell you, well, it's in the syllabus. Nobody ever holds a teacher to that, well, you got the holiday wrong. I'm going to take a holiday. It's in the syllabus. I never did stuff like that when I was an undergrad, but I thought it all the time. It's always a distraction. What can I say to... Okay, we're good, right? All right, we're going to keep going then. So that's resonance, and I'm going to cheat again. So I'm back to this guy. And I'm going to do something, I'm going to modify it a little bit. Get rid of that hydrogen. And put one double bond in. That's what it looks like. So that's nitrate. Overall charge -1. And you see how if you know the structure for nitric acid, nitrate, all I did was pull off a hydrogen and left the electrons.
Pulled out a hydrogen proton and left the electron.
Yeah, the proton transfer. I pulled that H off as a proton and left the electrons. Okay. So you'll notice what happened. I got more resonance structures that are equivalent all of a sudden. So you'll notice that by pulling that off, I have the ability to go like this. And where this structure before wasn't very good, it is now the same as all the other ones. And then the other Lewis structure would be this one. Let me circle the charges. If you don't circle charges, it's not like a sin the chemistry gods will not forgive you for, but it is, you lose charges when you don't circle them. That's the reason I circle them. So there's 3 Lewis structures equivalent to each other. So here's something you think about. This is what we generally say. The more resonant structures, equivalent resonant structures that a ion or formula has, the more stable it is. So more resonance creates more stability. Why is that, do you think? There's 2 factors, really, that we think about. There's actually a third one, but we're not thinking about it. What are the 2, like when I said F minus versus I minus, which one was more stable? I minus, right? Makes the stronger acid because the charge distributes better. More charge distribution. Yeah, you can distribute the charge over the entire surface. Why do you think more resonant structures makes an ion? It's the same.
I was going to say, from what I remember in 1A, is that when we draw these structures, the actual...
Oh yeah, the hybrid,
in
right?
real life is actually kind of constantly back and forth between all of us.
Yeah, it's the we call it the hybrid. It's like the average of all the structures, and that's actually what I'm getting to. You distribute the charge better over the entire surface, and so the charge density goes down, and as a result, the acid gets stronger. That's one, okay? So more stable because charge distributes over more of the surface. So I'm just going to write charge is more distributed. Looks like I've been drinking, but sorry. If I don't zoom in, my lines start to drift and letters get malformed.
Everything gets rammed in the corner.
And you're shoved in a corner, you don't realize it. Yeah. So remember, there's a thing called a resonance hybrid. It's like the average of all these, and I'm going to just go like this. It's trigonal planar because it's got 3 electron groups, and the charge we would draw like dashed lines like this. This oxygen over here, there's 2 negative charges spread over 3 atoms, so it's 2/3 of a negative charge. And each one of them has the same charge.
Oh, I see. Oh, that's cute.
And the positive charge is still sitting on the nitrogen, so I can just put it right next to the nitrogen. Yeah. So charge distribution is an important thing in determining whether or not an acid will be stronger or weaker. Okay. So I'm going to draw 2 Lewis structures quickly for you. I think I can get them right without thinking too hard. I'm not sure, actually. Well, yeah, I can do that.
Confidence there.
So let me go to, and you know, that stuff's all still there. I can go back to it if you want, but I'm going to go to another slide, and I'm going to do this. I'm going to draw nitrate versus nitrite. So nitrate's the same as what it was on the previous page. Nitrite is this. Of course, nitrous acid, the hydrogen would be hanging off this oxygen. Negative charges here. Now, the acid for nitrate is HNO3. Acid for nitrite is HNO2. Okay, so some of you already know the answer to this. Which one of those is the stronger of the 2 acids? NO3. That's the strong acid. HNO2 is the weak acid. Okay, that's just by memorization. Like the strong acids are the 8s of, and then you can list them all. Yeah. So think about this has 3 resonance structures on the left. So this is 2 resonance. Did you guys learn the stupid trick of like how you, on Oxxo acids, how you tell how many resonance structures there are? Count the oxygens. It's the number of oxygens. Oh my God, what? My teacher didn't tell me that. I don't think I told these guys either. The other. Yeah, you know, some things we got to keep secret until you're old enough. Now, what else is true about these 2 anions that would be significant in their stability? Size. HNO3 is, or yeah, the NO3 is bigger than the NO2. It distributes charge over more of a surface. So this is also larger. So as a result, right, it creates the stronger acid of the pair. So without even drawing Lewis structures, there's a lot of things that you can predict acid-base strength. For example, H2SO4 and H2SO3. Which is the stronger of the 2 acids? H2SO4. What's, yeah, by memorization, you know that, but now you know why. It's got more oxygen, bigger surface area, more resonance structure. Yeah, you can count to 4. Right?
Yeah, I can do that. We found the trick.
So, yeah, you know a trick. So 4 resonance structures versus 3, larger, better charge distribution, stronger acid. Okay? Okay, so let's do one other comparison. And I'm going to introduce you to something called the inductive effect. That was actually this, I think, the next part of this slide somewhere, but I don't know. Kind of wandering a little bit. Which one I did nitric? Yeah, let's do this. We're going to do ClO3 and BrO3. So we're going to chlorate and bromate. Okay, ClO3 and BrO3. And we're going to try to predict which one's the stronger, and then we'll sort of like think about the way we think about this. So I'm going to put Cl in the middle, and 3 oxygens like this. Oh, this is chlorate minus and bromate minus. I'm going to go through the process of drawing a loose structure because I don't want to screw it up, because I've been drawing this one a long time, and the tendency is I'll screw it up. So we'll just not screw it up. So oxygen, 18 electrons. Chlorine, 7. 18 and 7 is 25, but it's a -1 charge, so 26. Okay? So I'll write that out. I just did that in my head, though. So 3 times 6, that's for the oxygen, plus 1 times 7, that's for the chlorine, plus 1 because of the negative charge. I'm adding a negative charge, I'm adding an electron. That comes out to 26. So bromate and chlorate will both have 26 electrons. How many have I used? 6. So I'm going to have 20 electrons to distribute. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. And I need to distribute 1 more. So then go on the chlorine. Okay. So chlorine gets something to eat today. Okay, so now we're just going to leave it like that. There's formal charge problems here. This is a minus, this is a minus, this is a minus, and in the middle it's +2. How did I didn't calculate it the way you guys were trying to. How did I get that? Because I know it's a -1, and there's 3 negative charges on there. The only thing left has a +2 charge. Now in class, when I taught this in Chem 1A, I was pretending like I was calculating it, but I didn't do it. I just I lied to you. God, I love this job. It's probably the only profession where you get to be completely dishonest all the time, and actually people benefit from it. That's as a chemistry teacher. Like, biology teachers can't do this. They just tell you we don't know. And I'm just like holding stuff from you. No, yeah. This is, just think of it like this, and I'll tell you later. I guess I'm not lying, because I actually tell people I'm not telling you the entire. Yeah, I always tell you stuff like that. I'll tell you when you get a little bit older.
Yeah.
Which is true. You're a little bit older now, right? Or I pull out that line, the truth, you can't handle the truth. All right. So far, so good. They look exactly the same. Except for I forgot the line on the bromine. There we go. Exactly the same. And if you were to take care of formal charges, you would put double bonds between 2 of the oxygens in the bromine, and then you would violate the octet rule, but you would have a more stable structure that way. Okay. But we can do what we need to do from here, so I don't want to get into all that right now. So we're going to think about acids. We're going to compare HClO3 versus HBrO3. And let's talk about which one you think is stronger and which one do you think is weaker. And I'll tell you why the one is stronger and why the one is weaker. So which one do you think is stronger? The bromine one? Yeah, okay, we'll go with the bromine one. It's wrong. But it's the bromine. Let's say the bromine. Why do you want to say the bromine? Because of the size, right? Okay, but what where is the charge? It is bigger, right? So it is bigger, but where is the charge actually distributing? It's on the oxygens, it's not on the bromine. Right? So the relative size difference isn't that big. They're bigger, but it's not that much bigger. The oxygens are further away on the bromine, right? But the charge is residing on the oxygens. So then the question is, why is that not, why does that change the picture? And the answer is the inductive effect. Okay? So we're talking about inductive effect a little bit here. Then I'll show you some other examples. Chlorine is more electronegative than bromine, right? So it's not as electronegative as oxygen, but it's more electronegative than bromine. Now, the task that the oxygens have over here is to hold all this negative charge, right? If the chlorine is more electronegative, it can say to the oxygens, let me pull some of that charge away from you and distribute some of the charge to the inside. So the oxygens actually have less negative charge on them because the chlorine has a high electronegativity versus the bromine, right? So this charge that's here, let me draw it in a different color arrow so it'll show up. This charge is getting pulled in more, even though the chlorine's not as electronegative as oxygen. It has a better chance of holding that charge, and that lowers the charge density. So in all these oxo acids, the electronegativity of the central atom, not the size of the central atom, but the electronegativity of the central atom determines how strong the acid is. Okay? So
Negativity is more important than
size for oxo anions. Okay. Size is more important than electronegativity
Binary,
for our binary acids. Yeah.
yeah.
On a group. That's what we're talking about.
Yeah.
Yeah. So, if you think about the trend, HI is the strongest, but if you go HiO3 versus HBrO3 versus HClO3, HClO3 is strongest because of the electronegativity. Okay. And phosphoric acid versus sulfuric acid. Right? H3PO4 and H2SO4. H2SO4 is the strong acid, H3PO4 is a weak acid. Again, it's about, on a polyatomic ions, it's about the electronegativity of the central atom. And its ability to stabilize the negative charge cloud that ends up on the outside of that structure. Pulls electron density away, allows it to be more stable, lowers its energy. Okay?
And so then it takes less or more to release the hydrogen.
Yeah, it's easier for it to release the hydrogen to the water. Or in other words, it's easier for the water, for self-ionization, easier for the water to pull it away from the H2SO4 than it is the H3PO4. Even though H3PO4 has 3 hydrogens, right? Everybody thinks, well, it's got 3 hydrogens, it's got to be stronger. It's not.
Ain't necessarily so.
Not true, yeah. Okay, so that's an example of the inductive effect. That's a through bond effect. The through bond part is this. That causes these to be more acidic, okay? So this is, again, a classic example from organic chemistry that we talk about all the time in organic chemistry. So I'm just going to tell you now because then it makes my lecturing next semester easier. Those poor souls that walk in and I'm start talking about this stuff, they'll be like, wait, when did we learn about that? And I said, last semester. And I'm like, I wasn't with you last semester. Well, that's your problem.
Yeah.
Now I'll explain it to them again. You'll hear it again. I'm not that mean. I like talking like I'm mean, but I have a hard time with it. I like being found out in my life, being nice. A lot more miles on it.
You gotta be mean sometimes, though, so you don't go too soon.
No, you just have to be firm.
That's true.
You don't have to be mean.
Sometimes that's a little bit.
That's true, there's a difference.
Yeah, being mean is spiteful, doing things that you know you shouldn't do that don't help the situation, that are going to be detrimental towards somebody else.
Also be misguided.
Sorry. Life lessons in my class.
So that's,
Okay, so, and the left one's ethanol,
yeah. Here's two.
drinking alcohol. This one, do we know what this is?
Ester.
It's acetic acid.
Acetic.
It's what alcohol turns into actually when it gets oxidized. When wine goes bad and gets that sour taste, it's actually vinegar. This is vinegar, the acetic acid. It's why it tastes bad. Okay, so I forgot a lone pair or two. That's why you recognize. Yeah, of course. Oh yeah, that made all difference
Oh,
in the world.
yeah, well, now I got it, sure.
Sure.
So,
Okay, so I was thinking about quotes about wine. So, which one do you think is stronger? And then why? So,
I would say probably the ethanol, since the charges aren't as big.
I would say this over here is
Actually, no, hold on.
stronger because it has more oxygen.
this is ethanol.
Got that backwards.
This is acetic acid. So if I pull hydrogen off, this is how you do it. Think, what's the conjugate base? Well, how do we do conjugate base? Take a hydrogen off,
Yeah.
leave a negative charge, the hydrogen goes away with the positive charge, right?
Yeah.
So the conjugate base to this looks like this. Oops. And to tell whether or not one is stronger than the other, you got to look at both conjugate bases and think about all the things we just thought about. That looks pretty horrible, but that's okay. This charged, right, versus this charge.
Okay, I do the same.
The same charge, -1. What can this structure do that this structure can't do? Can have resonance. Right? It's an oxo acid. It's got 2 oxygens. I mean, you didn't recognize that maybe, but it's not. So it's got 2 resonance structures.
That's right.
So it's got resonance. It also has an inductive effect because you've got this other oxygen over here to help stabilize some of the negative charge, like pull a positive charge on this carbon, which helps stabilize this negative charge. Plus it's in resonance. But the extra electronegativity of the oxygen helps to spread that charge out better. So like, how important is this really, right? So it's got some inductive effect. So, acetic acid versus ethanol. Acetic acid is about 10 to the 10th times stronger. So what's 10 to the 9th?
Billion.
A billion. It's 10 billion times stronger. It's not a strong acid still, though. It's still a weak
right.
acid.
How many stuff they-
But ethanol is about the weakest acid you could have in water, and acetic acid is still considered a weak acid, but it's 10 billion times stronger than ethanol because it has resonance and a little bit of an inductive effect. Right? It's hard to imagine like that little bit of difference making that big of a difference, right? It's like I shoved it a little bit and the whole building fell over.
And again, just to sort of touch base here, when we're talking about the stronger acids, it means it's easier to break the hydrogen bond.
It's easier to separate the hydrogen from the oxygen. It's easier for the water or whatever is the conjugate, the base, to pull that off and form the conjugate base.
So, yeah, it's a weaker bond to the hydrogen.
Yeah, in essence, it's a weaker bond to the hydrogen, or because it becomes more stable. Go ahead.
Then how much stronger is HI than that?
About another 10 billion times.
Okay.
Yeah. So, but to get to the category of something that's a strong, so the equilibrium constant for for the acid ionization constant, the equilibrium constant for ethanol is so K. We're going to call it Ka, and I haven't spent any time with calculations yet in this class, but on Tuesday we're going to spend a lot of time on the calculations, and I'll finish up the chapter. All right, Ka for this is around 10 to the minus 15. Okay. Ka for acetic acid is about 10 to the minus 5th.
Okay, there's your billion.
That's even though it's a small equilibrium constant. Hi, if I'm remembering right, Ka is about 10 to the 7. You can't measure it. It's so strong you can't measure it in water. You can only get that by, you know what we talk about? It's the water that's pulling the hydrogen off. You have to get something that's not as good at pulling hydrogens off and put it in competition with the proton on the Hi to measure that number. So we don't use water because water is too good at taking that hydrogen away. So we use something that actually doesn't have a very free lone pair, doesn't have as much negative charge. Yeah, and we can measure it.
Is one like we use the methanol in other?
Yeah, you might use methanol instead of water, but that's actually turns out not quite good enough. So you have to use something like acetonitrile, or there's a bunch of things that you could use that aren't as good.
But that's quality.
Yeah, yeah. And if you don't know what acetonitrile is, okay, I'll teach you next year. Whew. Okay, one more thing I want to talk about, and I'm done. Oh yeah, actually, two more things. Sorry. Here's the other real simple thing to remember, right? If it's got more negative charge on it, it's weaker. So if you're comparing, for example, H2SO4 versus its conjugate base for acid strength, H2SO4, the reaction that we think about is H2O plus H2SO4, again, all aqueous or water is liquid, in equilibrium with H3O plus, hydronium, and HSO4 minus. Okay, that has a K value, but it's a strong acid, so I'm not going to write it down. And then H2O plus HSO4 minus makes hydronium plus SO4 2 minus. That has a K value with it too. Now this is called Ka1 and this is Ka2, but since Ka1 is big, we don't really talk about it.
Like water, close to water.
Oh, no. This Ka is like, if I remember right, like 10 to the 5th. It's big. So we don't really, it's basically fully dissociated, so we don't talk about the equilibrium in water. Because we're just talking about reactions in water. If it had been something else, then it has meaning, but it doesn't have meaning in this context. So SO4 minus, right, HSO4 minus and H2SO4, right, as acids, right, HSO4 minus is a weaker acid than H2SO4. Give me the reason.
Because its conjugate base is a higher negative charge.
Yeah, has negative charge. What is the proton when it leaves? Positive charge, right? More negative charge holds on to positive charge. So it's like I talk about sometimes. I have a candy bar, right, in each hand, and you want to steal one. So you steal one. Great. Maybe I give it to you. The next person wants the second candy bar. Now I've got two hands. I want to hold on to my candy bar. You can't have it. Especially if it's a Snickers.
Dr. K,
Almond Joy, not so much.
with this example, first equation you wrote was H2O plus H2SO4 in equilibrium with hydrogen and
Conjugate base,
conjugate.
hydrogen sulfate.
Does it matter at all if you were to do two H2O plus H2SO4? Would that not pull both of the hydrogens away to make two hydrogens?
It could, but it doesn't happen all in one step. Because the first one's really strong and it easily leaves, and the second one is weak, and so it doesn't easily leave. So when you have a diprotic or triprotic acid, you could write 1, 2, or 3, and you could calculate the equilibrium constant, for example, for all three.
This is almost like Born-Haber thing, where the more you've got to remove, the more energy it takes.
It is, oddly enough. Yeah. More things that you have to remove, the more energy
So I
it
see what you
takes.
say. The first one was a
Neutral.
neutral, so the first hydrogen it let go of pretty easily.
Yeah.
The second one, though, because HSO4 minus is a stronger, or weaker acid, it has a stronger hold on the hydrogen.
Yeah, because of that extra negative charge. Born-Haber process, when you took like calcium, they made calcium plus 1 and calcium plus 2, and you look at ionization energies, ionization energies increase as you remove electrons because what's left behind always has more positive charge. And it's always harder to pull a negative charge away from a more positive charge, just physics. This is kind of the opposite because you're having protons removed and leaving a negative charge, but it's the same concept. More charge, more traction, harder to remove. I really should stop. I want to just keep going. Oh yeah, I'm going to keep going. Just a little bit. So, sorry. Strongest acids at the top. Simple concept, I want to stop, okay? Weakest acids at the bottom. This is I don't know if this chart's in your book, but I stole this from a really old book because I like how now that we've talked about all these things, you compare acids and bases, acids to each other, and you can tell, down here, for example, here's HNO2. I can't control it. There's HNO2, right? There's HNO3 up here. It's the stronger acid, right? If it's HClO versus HClO4, HClO4 is the stronger acid. HClO3 and HClO2, where would you, even though they're not on here, where would you predict they would be? In between there somewhere, because of the degree of resonance that each one has and the charge distribution that each one can have. HS minus versus H2S, right? Why is HS minus weaker than H2S? Negative charge, right?
What you've been talking about.
Yeah, it's all
exemplified in that right
summarized there, and you could think of almost any two acids. There's bigger charts than this one, but any two common acids, think, well, I think this one's stronger than this one, and then look at that. Oh yeah, look, that one is stronger than that one. So you can go through and think about things like that.
This is good.
So then the other thing I wanted to point out is and this is general truisms, right, which are generally true, turns out. Yeah. So generally true that truisms are generally true, right? So HClO4, which is the strongest acid on this list, right, makes the weakest conjugate base.
That's right. One of the other things that you said was an axiom.
Yeah. Stronger acids make weaker conjugate bases. And then down here, weakest acids make stronger conjugate bases. And remember, when you think about it as an equilibrium, it's a competition between the acid and its conjugate base for that proton.
That's right. The ability to hold it.
Yeah, so you can't have a strong conjugate base with a strong acid, otherwise it would be a weak acid because it would grab that proton and reform itself. Okay. So this is a nice chart.
You get that on our test, right?
No. So it's a nice chart to be going through and thinking about acid-base trends. Good try, though.